the technology also works well with artificial intelligence, which is another upcoming topic. So we have more things to come in. So I would welcome you all once again to take this opportunity to dwell more into the prospects of additive manufacturing with the experts in the field. So before initiating the seminar, let me take some time to introduce ourselves. As you may be aware, CIPET, Central Institute of Petrochemicals Engineering and Technology, it's a premier national institute under the aegis of Department of Chemicals and Petrochemicals, Ministry of Chemicals and Fertilizers, Government of India. We work towards excellence in main domains of skill development, technology support services, academics, and research. So earlier we were concentrating more on plastics. Now we have broadened our area into petrochemicals. So through 41 centers and few more in pipeline, CIPET is looking forward to carve a niche place in petrochemical domain as well. So not taking more of your time, we would like to give a small introduction, which my colleague will be doing, to the School for Advanced Research in Petrochemicals, CIPET's R&D wing. Our first speaker would have been Dr. Joseph Bensing, who heads this Bangalore Center as senior scientist and head. He is basically a mechanical engineer with 26 years of experience, specialized in the field of product design and development. And he has established the product design facilities here, CAD design, validation and optimization, industry type, additive manufacturing technologies, who is very very much working towards product validation, tolerance, geometric design, dimensioning, manufacturing, assembly, everything. But unfortunately, due to some unavoidable circumstances, he is unable to join. So in his place, I'd request one of my another colleague, Dr. Wasim Firoz, a scientist at CIPET SAP APDDRL. He currently focuses his research interest in the area of membranes for fuel cells and recycling of plastics. He is also actively involved in this additive manufacturing and product development area also. So with a background in polymer engineering, he has completed his PhD from IIT Bombay and Monash University in specialized area of membranes for fuel cells. Here at CIPET, apart from his core activities, he is looking after consultancy projects, basically in the area of additive manufacturing and recycling of plastics. Dr. Wasim, over to you.
Thank you, ma'am. I hope I'm audible.
Yes, you're audible.
Yeah, on behalf of CIPET, I welcome all of you for the short industry meet. As Lakshmi madam said, like CIPET basically, just a second, I'm just sharing. Can you see my presentation?
No, sir.
Yes, it's a.
1 second, sir. Yeah, is it now visible?
No.
Yeah, I think now it should be visible.
Yes.
Yeah. Just a second, I'm unable to shift the slide. Yeah. As Lakshmi ma'am said about CIPET, it was like established about 50 years ago, and mainly it was established as a tool room. Then later on, it started doing skill development and technology support to industries, academics, and recently in the past 1.5 decades, we also ventured into research and development of plastics and even product design. Basically, we have 41 centers all over India, as you can see. and it's divided into main three categories. That is IPT, Institute of Plastic Technology, and CSTS for Skilling and Technology Services, and the R&D wing is SARP, School for Advanced Research in Petrochemicals. Basically, we have three centers. One in LARPM, it was first established in 2008. It deals with the material development, and we have ARS TPS. It deals particularly about design and product development. But the Bangalore Center was particularly uh, established for basically for research in both material development and also product design and development. So this one is an exclusive institute set up mainly for the purpose of R&D. As you can see, the three categories of our institutes cater to different levels of teaching and academics. Like CSTS deals with the diploma courses, IPT deals with UG and PG programs, and the R&D wings are mainly concerned about the higher programs like MTech, Masters by Research and PhD. Today I will be focusing only about the Bangalore Center. We have established laboratory here, which has been accredited by NABL, NABCB, and other national bodies, and we support almost all kinds of industries for their requirements in testing and characterization for plastics and polymers. In CIPET Bangalore, I will be covering these basic topics today. That is what all we do here, apart from research and development, technical consultancy, technical support services, and even specialized training, and PhD and MS by research. So the sole purpose of the center was to set up as a one-stop facility for both design, product development, material characterization, processing, simulation, and product validation. So here we have both the all high-end software for designing, machinery for prototyping, and also laboratory for developing materials. So these are the few areas in which we deal about, like biopolymers, composites and nanocomposites, plastics recycling, coatings and adhesives, and polymer electronics, design optimization, rapid prototyping, reverse engineering, etc. So some of our research consultancy services cover the following areas, wherein we have specialized experts doing research and consultancy projects on the following topics. Example, like bio-based composites and materials. Here we are focusing mainly on the packaging material, which is being developed through bio-based materials. Currently, we are running 2 to 3 projects on this for developing eco-friendly packaging material. And then we have.
I will call you back. I'm meeting, so I will call you after. Okay. Okay.
In the area of coatings and adhesives, we have our expert scientists working on development of super hydrophobic coatings, anti-fouling coatings, weather resistant coating, etc. And when it comes to energy related research, here we have 3 to 4 scientists working particularly on energy materials, basically development of catalysts, development of membranes for fuel cells, batteries, etc. And even we have 3 scientists working on the membrane technology. It's a very hot field in nowadays. The membranes which cover filters for cartridges, membranes in PEM fuel cells, membranes for rear lithium-ion batteries, separators, etc. We have all the setups for checking for developing both membranes and also checking the properties of the membrane for the efficiency of it. Then, as CIPET has been involved in the past 50 years in plastic, so we have a duty to take care of the end of life solution of the plastics. So we are also working on to provide solutions to the industries on the different types of plastic waste, such as MLP, multi-layer packaging, single-use plastics, biomedical plastic waste, and currently we are running 2 projects basically on value addition of biomedical plastic waste. And then we have the product design and development area, where we have all the softwares, reverse engineering hardwares, prototyping machines, and even the all the new development areas. These are some of the products developed by our scientists, not in this center, but in the previous center where we worked. So these are some of the products showcased on the outline. When it comes to technology support services, apart from providing the testing services, we also take care of the basic consultancy services for analysis of the material, even the product. So if any industries has any issues or any defects in the problem, facing any problems in their processing or development of product, then they approach us and we provide them solutions for this. So we have all the testing equipments which cater to the mechanical testing, life cycle analysis, morphological analysis, thermal analysis, and other high-end spectroscopic studies. And one more very hot area is the biodegradable material. We do the testing of these materials. We follow the standard of ISO 14855, and we do the testing for the 6 months testing, wherein we evaluate the performance of the material under compostable conditions. And one more important area is the life cycle of the plastic material, like how many times the material can be recycled to be put in good use, either in the same application or in any other value-added addition. So we also we check the material for its number of recyclable properties. I like do the analysis such as the FTIR, DSC, TGA, and find out the properties of it, how the property is varying with each cycling, and then we can suggest in which all products it can be used. And as I mentioned before, we have the following facility for the reverse engineering, product development, design, and example, this one, vacuum casting machines we have. In 3D printing, we have the FDM machine. So let me just take you to some of the facilities what we have at our Bangalore center, which is now fully established. So these are some of the high-end machineries what we have in Bangalore center, like for basic characterizations of such as FTIR, FT Raman, rotational rheometer, XRD, TGA, particle size analyzer, mesorometer, etc. Then for bio-based materials, we have this torqueometer, blown film producing machines. Then we have GPC, micro compounder. We can also use very small amount of material for micro compounding and producing samples. Even if we have around 10 to 15 grams of material, we can do the compounding and produce samples for testing using our micro compounder and micro injection molding machines. And then in coatings, we have the specialized equipment such as spin coater, goniometer for checking the contact angle, then volume and surface resistivity, mechanical devices such as to measure the lap shear of it, and basically for films, we measure the coefficient of friction tester. And we also have a high-end equipment FESM, which has been installed recently. Then for compounding facilities, we have a tin screw compounder, rheometer, injection molding machines for making samples. We have an 80-ton machine which can easily produce some small samples. Then for the membrane process, we have our electrochemical workstation. We have forward osmosis setup, reverse osmosis setup, where we can check the properties of the developed membranes in-house and tweak the properties. In 3D printing, as I mentioned before, so these are the this is the machine what we have, this FDM machine, which can easily print up to 300 to 400 millimeter parts, and a vacuum casting machine, which has a bed size of 750 to 900 mm. And for the testing the products, we have a axial torsion fatigue tester, which is a high capacity machine which we can use for testing both plastics, composites, and even metals. It has a capacity of 100 kN. We can do all kinds of testing such as torsion, shear, and bending fatigue, and even we can do it in a like specified chamber, the temperature of -150 to plus 300 degrees Celsius. Apart from that, for mechanical testing, we have this pin on desk tribometer and vibration lab, where we can find out the resonant frequency of the either material or even the product. And apart from this, we also conduct specialized training programs which cover the following topics mentioned on the left side: plastic materials, plastic processing, biomaterials, waste management, functional materials. The topics are not limited to this, but even if the industry comes up with any tailor-made areas, for that also we can cater. Even if we don't have any experts in the particular area, we approach our experts from the neighboring centers or industries, and we give them training on those topics. And we also conduct the design program for CAD/CAM. We have software such as ANSYS, SolidWorks, Mold, this Moldex 3D, and other CAD/CAM softwares. And basically, we are registered as a recognized as a research center from BTU, and we are already running this MSc and PhD program, and we will be starting this MS by research program in the coming academic year. And these are some of our major customers through which we regularly serve, and we have this NDA with them. And before handing over to the next speaker, I would like to just showcase a small video of our center. Is the video visible?
Yes.
Thank you for your time.
Okay. Thank you, Dr. Wasim, for taking everyone through our facilities and infrastructure. And on behalf of CIPET, we'd like to tell that we look forward to associate with all industries in whatever areas possible in the domain of petrochemicals and serve our provide our best of services every time.
Yes, yes. And I think not many people know that CIPET is in Bangalore because it's a
Yes.
surprise for many people. We are located near the airport. So if you can just check in Google, you will find the location exactly. So if you have any issues related to the plastics, processing or design related, you may contact our team.
Yes. So thank you, Dr. Wasim, once again.
Thank you, ma'am.
Yeah. So I think we should move on to the next speaker. We have career as a management trainee, technical services at in 2017, he moved back to India and has since been leading countrywide operations for digital manufacturing for Altum Technologies. Abhishek comes with nearly 8 years of experience working with various additive manufacturing technologies such as FDM, MJP, SLS, DMLS, etc., and has executed products in various industries such as healthcare, automotive, and aerospace. He has also taken up many consultancy projects with clients of various countries such as South Africa, India, Saudi Arabia, and Namibia as well. So I take this opportunity to welcome Mr. Abhishek Kalra to provide us more details on advances in this field.
Thank you so much, ma'am, for the kind introduction. I hope I'm audible to everybody.
Yes, sir, you're audible.
Okay. I'm going to share my screen. Yeah. Okay. So, good morning, one and all. I am Abhishek, representing Altum Technologies, and today we're going to talk about functional and performance applications with 3D printing. Now, whenever we talk about 3D printing, we have a common misconception that 3D printing is only possible for basic design validation and prototyping. That is not the case. Today, with advancements in materials and technology, we have been able to take 3D printed parts into actual production scenarios and do testing on 3D printed parts in the same manner as how we would do it with conventionally manufactured parts. Before I show you some of the work that some of our customers and we have done in this area, just like to give you a small introduction about our company. So Altum started in 2011. We started as a 3D innovation platform company. What that means is that we have products and services that are that enable customers to go from their idea to product, ranging from design solutions, from Dassault systems, simulation solutions, from MSC software, 3D printing solutions. Today's presentation, which is going to be more or less on this subject, as well as 3D scanning solutions. Over the course of our journey, we have won several awards. We were awarded the most innovative 3D printing company of India by Frost & Sullivan. We are in the top 100 SMEs, so on and so forth. Our customers include some of the top names in various industries. And now this is a very interesting slide because it tells the kind of industries that are taking advantage of this technology. It's not only the engineering community, but also healthcare, for example, or IT services or electronics, and of course, education institutions. And we are very proud that CIPET is one of our esteemed customers as well. Now let's get into the topic. Now, 3D printing is not something that has been new. It's been around for more than 30 years. Scott Crumb, founder of Stratasys, invented fused deposition modeling back in 1989. Was one of the first 3D printing technologies to get available in the market. And back in the day, this is what a 3D printer used to look like and still cost tens of thousands of dollars, which could only be able to produce tiny parts in very, very basic materials. But then back in the day, it was a stepping stone to a revolution that has now come. But as you know, we have in the past 30 years, we have gone to now several hundred different types of materials that we can produce, ranging from basic materials to extremely strong materials, which are now replacing even metals in certain applications. Part sizes or sizes of the machines have grown exponentially from a small, maybe 2 centimeter by 2 centimeter or 2 inch by 2 inch build size to a 1 meter bed size. And today, the industry is moving towards a trend where 3D printing is being used for low volume manufacturing also as a combination of both of these attributes, that is size and materials. Now, because of, as ma'am also mentioned and sir also mentioned, that one of the key benefits of 3D printing is that it can produce parts with any or every geometry or any or every kind of complexity without you having to worry about how you will make this part. When we were studying engineering, we were always taught how to design parts as per the manufacturing process. And in that process, sometimes we would lose some of the benefits of a better design because we did not have the capacity or the capability to manufacture it conventionally, or it'll be too expensive or too cumbersome. But because 3D printing can produce any geometry, sometimes which is something which is not even possible even if you combine multiple technologies, that makes it suitable for many applications. So in principle, any industry that requires any type of parts, whether it be one number or whether it be 1,000 number, or whether it be one design or tens of designs, can use 3D printing. Some of those industries, automotive, aerospace, white goods, healthcare, drones and robotics, you name it, 3D printing is almost everywhere. Now, let me introduce the technology that CIPET has, and it has been one of the most successful 3D printing technology. This technology is called fused deposition modeling. On the screen, you see a machine called Fortis 450 MC, which is one of the production grade 3D printers offering from Stratasys. Same machine that CIPET Bangalore has. And the reason why this machine is successful is because it enables you to produce as complex as possible parts, but more importantly, real world thermoplastic materials. What that means is that the properties of the materials that you get out of the 3D printer will be very close, maybe around 90% close to what you will get with conventional manufacturing. Most other 3D printing technologies use synthesized materials, which can give you complex geometries, but are not able to give you the exact strength of material or the exact properties of the material as your conventional manufacturing methods do. As a result, you can use these parts as replacement parts to some of the conventional manufacturing processes, as well as even use them for real world testing. Now, how it works is very simple. I'll explain it through a video. One second. So this is a small video which will explain how FDM works.
In a word, it's a game changer.
It can create parts and geometries that you can't do in an injection molding.
That's going to create a revolution in the near future, and this technology be adopted as a major process for manufacturing components.
So FDM stands for Fused Deposition Modeling.
It's a fancy word for laying down a small bead of plastic.
What's really cool is you can have a real engineering grade thermoplastic. So the same stuff you'd injection mold.
If someone needs an ABS or a polycarbonate or a high temperature Ultem, we can actually print it directly as opposed to casting a part or having injected molded parts done.
You're getting close to the same quality in mechanical properties and aesthetics as you would an injection molded part, but you're getting it in an additive process.
Our software takes a 3D data file and it slices it into layers. Then that creates a tool path that's sent to the machine.
The raw material is produced into filament-like fishing line type form. That filament is wrapped around a spool, so that's your cartridge of raw material that's going to be used to build parts. That material then gets fed up through the machine all the way to the head, where it's liquefied and extruded in fine layers. The support material is extruded at the same time, and then layer by layer the part is growing. When the part is completed then, it's removed from the build platform, and then the support material is removed. We also offer post-finishing operations that can smooth out those layers. So whether it's a hand finishing or cosmetic paint, we still can provide smooth looking parts.
We developed the technology to fit a full breadth of geometry sets.
We've seen it used anywhere from small prototypes for mock-ups on test fitting parts to really large structural pieces that go on airplanes or UAVs.
We've gone from that, we're just doing real easy concept models, onesie twosies, to now we're doing production runs of 5,000, 10,000 parts that are, and it's the actual part coming from the FDM technology.
And so with it, we can do things that I have yet to even think of, but that younger generation, they're going to take this FDM process and turn it into something it's going to blow me away someday.
Yeah, so that essentially explained to you how FDM works and what are the kind of materials that we can produce. Now, one of the key benefits of this technology, as I explained earlier, is the fact that we can do real world materials. Today, we have about 15 different types of polymers, super polymers, as I like to call them, that we can produce, ranging from your basic materials, which can be used for prototyping applications such as ABS, but also electrostatic dissipative materials, which are very suitable for conductive or electronics applications. We have high impact materials such as polycarbonate and PCABS. We have strong but flexible components, materials such as nylon. And then we have the high performance materials such as the Ultem polyethyramide, PEC polyether ketone, and carbon fiber reinforced materials. All of these materials are fire resistant, chemical resistant. They have temperature resistance up to 220, 230 degrees centigrade. So these materials can really be used in applications where where complex geometries are required, but also functionality and strength is required. Whether it be smaller parts or whether it be very large assemblies where you can print the parts in sections and then assemble it together, it doesn't really matter. Some material properties are on the screen for you to take a quick reference. You can take a screenshot of the slide if necessary. However, I think we'll send a white paper as well. So some of these materials, for example, Ultem 9085 and Ultem 1010 are aerospace certified materials. What that means is that they are pre-approved by FAA to be used in aircraft. Our Indian aircraft, satellite, and missile manufacturers are also using these materials to put parts on aircraft, satellites, and missiles. But then beyond the aerospace industry, this material is fire resistant and chemical resistant. So even if you are not an aerospace company, but have requirements of high temperature or fire resistant materials, you can use it. Another very interesting material is nylon 12CF, which is 35% chopped carbon fiber weight by weight with nylon, which can produce parts which are even stronger than aluminium. So the stiffness to weight ratio of this material is better than aluminium. So we have a lot of customers who are replacing conventional aluminium parts, which are bulky and heavy, and with 3D printed part. 3D printed parts, and they have been working very, very nicely. Now let's look at some of the success stories of 3D printing. Now this this image is a very good example of what you can do with a 3D printed part. This is from the automotive industry, where you can see an exhaust manifold being mounted on an actual engine. This particular part actually was done for a Formula One car. And you can imagine that a Formula One car has, excuse me, more a very high stress environment as compared to real car. So as compared to a normal passenger car. So it works at very high speeds, it works at difficult tracks, so on and so forth. The aerodynamics is very different. And we were able to print a part, this is printed in Ultim 1985 material, and run it throughout the entire season for a commercial Formula One application. So that's sort of the epitome of what 3D printed parts can do for you. They can work as good as conventional parts, but you can have a part like this in hand in a matter of 24 to 48 hours, as compared to 6 to 8 weeks or 5 to 6 weeks that you will require to produce it conventionally. Now, typically 3D printing can be divided into 3 applications. Application number 1, which we all know, is design validation. You are designing a new product and you want to see how your design looks like, feels like, and fits like. You can quickly take that CAD, put it into the 3D printer, it will create a prototype. In a matter of few hours, you can use that prototype and check your fitment. But that's not enough. Today, industries need prototyping to be not just design validation, but also functional validation. So with the help of the materials that I told you about earlier, you can actually print the part, put it on the real world test scenario, and run the test as you would do it in the real world scenario. The next application is manufacturing application. Now, what if you have complex designs but low number of parts? One example on the top of my head is drones. Now, for those of you who are coming from the drones industry, drones is a very custom application. While the drone body might be same, drones are today being made in a way that they can be heavily customized. So today you want to put a camera on your drone. Tomorrow you want to put a heat sensor on your drone. Third day you want to put something else on your drone. So you can't keep buying new and new drones every time. So for those applications where number of parts are low, maybe 500 or 1000, 3D printing can be directly used in end-use part scenario. But what if you are in a scenario where you have either very large number of parts, of course, high complexity parts, or you want to produce a part in materials that are not available with 3D printing. And that's where the application of rapid tooling comes in. As I've written on the slide, it is a way to bridge prototyping and manufacturing. Now, let me take an example. Let's say you want to produce a part in, say, cast iron, right? But you don't have a printer that can print cast iron. So what we can do is that we can 3D print a pattern in ABS thermoplastic and then use this as a master pattern for investment casting or sand casting process. Now it takes me 6 to 8 hours to produce a pattern with 3D printing, and then probably a days of work through the investment casting, and within a day or day and a half, I have my metal components ready in my hand. Where 3D printing provides you the complex geometries and investment casting provides you the material. Or for example, you want to make 1000 parts, but you don't want to print the same part 1000 times. So you can make master patterns and then using vacuum casting or silicon molding techniques, replicate that master pattern into a number of parts. Also a facility that CIPET Bangalore has vacuum casting facility. So tooling is one of the areas where you can combine the benefits of 3D printing with the benefits of conventional manufacturing and get the best of the both worlds. Of course, in a more cost-effective and time-effective manner. Let's look at another video which shows you how 3D printing parts are being used in the manufacturing scenario in a very high-performance application. This is from automotive.
My name is Craig Kruckenberg, CEO of Minimizer. We are a manufacturer of plastic truck parts for the heavy truck industry. We've been in business since 1984.
Here at Minimizer, some of the projects that we work on are injection molded components, and primarily right now we're looking at several mounting brackets. A lot of these parts are made from glass fiber and rough, rugged plastic materials, and so it's a challenge to prototype those products. With the black Ultim material, it's very high tensile strength and rigid. We found that the black Ultim is a good alternative for us to prototype these mounting brackets and even take them out into the field on a truck and test them out. When we make an FDM part, we mount it on a truck, so a lot of times there'll be a lot of drilling, using fasteners, even mating parts together. The black Ultim material is valuable because if there needs to be any sanding or cutting of the part, it allows us the flexibility to do that, but still have an aesthetically pleasing part to put on a vehicle.
The reason for the black Ultim, and we're excited to see that, is that's 90% of the color of my product in our industry. We caught one of our OEs actually using the product in road trials with the Ultim, and they decided that, you know what, in this application we don't need that many to tool up for it, so if you could just print us out 15 of these, it's for a military contract and they just need 15 units right now. So we said, okay, give us that part back, we'll give you the Ultim in black. And so that's when we found out that this came out. We were going to paint it, but now that it's coming out in black, we don't have to worry about the paint.
Having the black material is a big bonus for us. We don't have to spend the time to finish the part, and at the same time we get the same material properties that we look for in the Ultim material.
Yeah, so again, this video shows you how a commercial automotive company, a truck manufacturer, is taking 3D printed parts and using them in high endurance scenarios where the part has to go through all sort of mechanical loads and stresses, and it is strong enough to be used as an end-use part, solving not only a technical challenge but also a commercial challenge, that how do you make parts when you have very low numbers and tooling is not justified. Another example is from a pump manufacturer in India, where as you can anticipate, or even if some of you are from a different industry, I'll tell you that the profile of the pump, this profile of the pump, determines its efficiency, and that's the parameter that has to be tested. So what this company does is that instead of waiting 3 weeks or 4 weeks to have a sand casted pump in hand, they produce 3D printed prototypes, test it in real world conditions, 3000 kilopascal of pressure at about 30-40 degree temperature, and on the basis of that they are able to get an idea of whether their profiles are correct or not. That's not it. They also use the same 3D printed part then as a subsequent master pattern for sand casting. Take the 3D printed part, create a metal part out of it using sand casting, and then use that for the further testing. So within the same prototype, not one but two challenges are being addressed, and they are able to get their complete process and testing done in a matter of 2 days or 3 days at substantially low cost as compared to 6 or 7 weeks as it would take in conventional tooling based methods. The third example is from DRDO here in Bangalore. Now, this is the Center for Artificial Intelligence and Robotics. Now, these 3 robots that you see on the screen are 3 among many that are actually 3D printed, assembled, and finally used in military applications. Robotics has been playing a very important role in warfare. Like the center snake robot that you see, it can climb up onto pipes, it can move onto all-terrain surfaces, it can go inside thin tunnels, so on and so forth. And this is complexity of design which is very difficult to produce using conventional methods, or it will be too costly to produce. So CAIR prints the parts, assembles all the electronics, and uses them directly as end use robotics. And as you can imagine, a robot which is being used in an induced scenario will go through a lot of wear and tear, but these materials are strong enough to be able to handle that wear and tear and run successfully and sustainably in all sorts of environments. Another example I'd like to give you, and I think this is the last or the second last slide, is from a replacement part application. Now, very often, what happens is that several industries have parts on their products which are either too old and the supplier base does not exist for that part, or it is too costly to import or manufacture that part. So what we did here is that this is from a submarine application, where the part was completely rusted and corroded and no longer fit to use. As you can see, the holes have completely damaged and the surface is completely abrased. So what we did here is we 3D scanned this product, reverse engineered it because no drawings were available. And for the time being that the tooling was being ready, which was about 4 to 5 weeks, we 3D printed the part in carbon fiber material, sealed and painted it, and actually deployed it onto the submarine. So till the time the part was being ready with the conventional material, a 3D printed part was being used as the replacement material and it ran successfully. But we have also customers who have completely replaced conventional manufactured both metal and polymer parts with 3D printed parts on applications where it's very expensive or difficult, if not impossible, to get the original part or original material. An application, very classic application in the defense industries and the special purpose machinery companies who often import parts from their OEMs based in Europe or US. Let me skip this. Let me also skip this in the interest of time. Now, this is interesting. This is going to be my last case study. One of the very important or very, very useful benefit of fused deposition modeling, FDM, is the fact that we can produce parts which are hollow from inside. This not only enables us to save weight and the hence cost, but it also enables us to integrate certain features from inside the product. Now, what you see here is an end of arm tool. The purpose of this tool is to hold a glass fiber sheet and in position during a water jet profile cutting. Now, if you look at this part, which is the conventionally manufactured part, you can see it's very bulky and there's a lot of things hanging around to the part, motors and vacuum lines and so on and so forth. So what the customer did is that they re-engineered the part and had all the vacuum lines go from inside the part. So there is a hollow channel that is going inside the part through which the inlet outlet vacuum line goes through. The weight of the robot was reduced from 16 kg to 1.5 kg. The lighter the robot, the faster it can move. The manufacturing time was cut down from 20 days to 3 days. And there was approximately an 85% cost saving. So those of you who come from the manufacturing industry and have a lot of robotic lines running on the factories, end of arm tooling is a very, very interesting application of 3D printing. And you can get in touch with us and CIPET, where we can help you re-engineer or redesign the part and take the most benefit of 3D printing, save costs, save time, and make your factory smarter and more efficient. I think with that, we come to the end of the presentation. Thank you so much for all of you for listening to me so patiently. If you have any questions, I'm happy to answer.
Yes, Mr. Abhishek, Mr. Kalra, thank you for the nice presentation. And it was indeed enlightening to understand the prospective applications of additive manufacturing in like some of the most unimaginable fields in very, very high-end applications and sophisticated sectors.
Thank you.
So yeah, so I think we'll have the next speaker, and once he is also completed, we'll have the question answer session.
Sure.
Yes. Uh, so moving on, let me call upon our next speaker, Dr. Yenam Ravi Kumar. He is an associate professor in mechanical engineering department at NIT Warangal. He obtained his BTech degree in mechanical engineering from JNTU Kakinada in 2000, ME in computer integrated manufacturing from PSG College of Technology, Coimbatore in 2002, and completed his PhD in mechanical engineering from Osmania University, Hyderabad in 2011. He also has postdoctoral research experience in 3D printing at Milwaukee School of Engineering, USA in 2012. As of now, he has supervised more than 35 MTech projects, produced 5 PhDs, and 5 more are in process. He has also published more than 80 research papers in national and international conferences and journals. He has filed 1 international patent and 2 Indian patents, all in the area of 3D printing. He is very instrumental in setting up rapid prototyping laboratory at NIT Warangal and started MTech program in additive manufacturing in collaboration with Central Manufacturing Technology Institute, Bangalore, for first time in India. He has established a world-class metal 3D printing facility at NIT Warangal under the TechUp 3 grant. He has conducted more than 16 training programs across India and trained around 1,000 participants in the area of 3D printing. He has received the Young Engineer of the Year 2009 award from the Government of Andhra Pradesh and the Institute of Engineers India. He has executed sponsored R&D projects worth of 1.24 crores in the area of 3D printing itself. He is the life member of ISTE, IE, RPSI societies. He visited countries like Australia, Sweden, Singapore, Finland, France, and USA. Professor Ravi Kumar?
Yeah.
Yes,
Am I audible, madam?
Yes, sir, you are audible.
Yeah. A very good morning, and Dr. Lakshmi for your introduction, and Dr. Ben Singh, from Dr. Ben Singh from CIPET Bangalore, and my co-speaker Dr. Abhishek from Altem, and Status is sponsoring this event. So very good morning, one and all. So I may be a bit odd man out here. I may be the academician. I am not from the industry background. Yeah, let me share my screen. Hello.
Hello? Yes, sir. Your slides are visible.
Okay. So let me go to.
Yes.
Yeah, thank you. So let me give some time. Yeah. Yeah, my talk will be on the design for additive manufacturing. Let me first thank the organizers of this event, the Altem Technologies, Stratasys, and CIPET Bangalore, giving me this opportunity here to address the gathering. So my presentation may cover a quick introduction to additive manufacturing, and then design approaches in additive manufacturing, and bit of AIM processes at a glance, not in detail. And most of the time I will be concentrating on the things that AM is unique in some of them, like the previous speaker has already given case studies about the some of them may be part consolidated parts or conformal cooling channels, and topology optimized structures, and bionic designs. So these are the unique capabilities of AM that you could even enhance the capability of the products that we are going to see. And we have a lot of importance in simulation of these additive manufacturing processes. So we'll spend some time on the build simulation kind of stuff, and design rules for polymer AM as well as the metal AM design rules, which I'm going to discuss with you. So this is the agenda for the presentation. So as we know that now we are in the industry 4, that's the fourth industrial revolution. So where you have migrated from the first industrial revolution to steam power mechanical production systems, that is in 1780s to 1860s, and where second industrial revolution was assembly lines, electric power, that is 1870s to 1960, and whereas the third industrial revolution predominantly computing, IT, and automation electronics during 17 to 2010, and where now we stand in industry 4. And you have other, say, the spokes of this wheel of industry 4. So where you have autonomous systems, cloud computing, system integration, and you have simulation, IoT, augmented reality, big data, cyber security. And coming to the manufacturing, now it's getting shaped into an additive in nature, and a lot of studies. And there will be a lot of hype or expectations. And a lot of surveys are saying that it's going to be the future technology, rather than in industry 4.0. The additive manufacturing, the manufacturing is getting shaped into additive. So with this background or the importance of this additive, why we are now assembled here. So, and I think the previous speaker has given the basic principle of FDM-based system. And let it be any technology, but these 8 steps remain same, which we need to start with our product to modeling of it. So design should come in a digital format like a CAD system, or even it come from a reverse engineering or medical CT MRI scans, but it should come as an STL file. That is the de facto standard for additive manufacturing to understand your AM machine to say understand this STL file. So then we need to then send this STL file to the interfacing software which is connected with your 3D printer. So then we need to set up the parameters, like if it is a laser driven system, so we need to supply the laser power, the scan space, and other parameters. And if it is other like extrusion based system, which we need to set up those parameters and orientation, support structure. So all that should be done here. And once you set up the file, or that codes will be sent to the machine. So where the physical realization of that digitally sliced components are getting realized in the say machine, and then we have to remove the part. Means we need to clean the part, and support should be removed, and we need to do a post processing here. Further, you are not satisfied with the properties that you are getting from as built component, and even it could be even subjecting to some kind of furnace treatment or some side of say shipping operation, or some sort of say finishing operations can also be performed on that in order to get your required say properties. So then your application is ready here, right? So these are the typical 8 steps that any AM process it should undergo. So then why additive manufacturing? So why can't it be a conventional manufacturing? So definitely your additive manufacturing is going to give an opportunity here to enable a new geometrical shape. For example, if you come from a tool industry, like where you have the concept called conformal cooling channel. So whereas your AM will enable you to manufacture these kind of conformal cooling channels, which is confining to the shape of the component, that is not done, or it is impossible through a conventional manufacturing. If at all, if you do a conventional manufacturing, so it may be a very costly affair. So why? Because your complexity is once increased, so your cost is exponentially increased in a conventional manufacturing methods if you go. But whereas additive manufacturing will leverage it, or your cost will be same irrespective of your complexity, and at the same time you are going to get the double benefit that you are going to improve the performance of the product. So you're getting at the lower cost, as well as your performance is also improved. And whereas your new geometrical shapes has been enabled because of this technology, and cost is also reduced, right? So as ultimately your tooling industry, like where it is looking for your cycle time should be reduced, right? So ultimately your cycle time has been reduced, that you have integrated this technology in your industry, right? So with this background, so So then what is the design approach here? Like say, can it be a conventional design? Can it be given to the additive manufacturing machine, or we need to tweak the design, or we need to modify the design? Or if at all, if you want to do, then why you want to do that? So for example, you take a typical manifold here. So this manifold, which you can see on seeing it, so one can understand it is meant for a conventional manufacturing method. Absolutely, it's not meant for an additive manufacturing methodology. Why? Because this design says that it's more bulky. It's like a block of say thing, and where it may be a much encouraging if you go with the conventional manufacturing method. So, but if you want to simply say reproduce this design on an additive manufacturing process, so probably it may take 4.6 kg. And say if you modify the form, so if you modify the form, so then even so you made this the block design into a shell-based design. The previous speaker was mentioning, like, so we can cut down a lot of say weight. Even that is the thing where you have made this say solid into a kind of you have changed the form here, and where you could be able to reduce the 4.6 to 1 kg. So that is 78% weight reduction. And further, if you understand the design for additive manufacturing concept, so means further what you are trying to do is you are modifying not only form, you are modifying the function, you are modifying the fitment. So where now 1 kg is now it's a 0.4 kg, means if you compare from the original, it is 91% reduction in the weight, and also it improves the fluid flow and also the fitment and more compact in size here. So you have that kind of advantage, like you can fix it in the less space, and this product and is easily assembled, right? So you are going to get this kind of a benefit once you migrate from the conventional manufacturing to say additive manufacturing. So this is one observation where your design approach of your additive manufacturing so should be somewhat tweaked to this. And further on that discussion, say you have a solid block manifold, and if you do this a kind of a solid block design, and the scan time for, if you do it on a metal machine, probably this is on the metal machine, so the scan time for the hatch pattern here is 191 hours. So, and the machine cost, it may be the 1 hour if you use, and $65 means it is a $1,200 that is the machine cost. And we have to add the material cost. The material is 7.4 kg, and if you 70 kg, 70 rupees, $70 per kg, and this is say 316L stainless steel, and it will cost you like 15K, say approximately. That is the cost if you go with this design, the solid block design. But if you tweak this design from solid to a shell block kind of a manifold design, and now your scan time is 36 hours. So now the machine cost is reduced now accordingly. And now the material weight is now 1.2 kg. And further you have saved in terms of material cost. And the service bureau, the quoted you 3735 is the cost that has been quoted by the service bureau. But further, if you could able to optimize this as per the design guidelines of additive manufacturing, so maybe considering your orientation, supports, all that can be taken care. And then further optimization and further saving has been done. Now the scan time is only 19 hours. So means your machine cost is 1261, and now the weight is 0.5 kg. Again, you are able to reduce the material cost also. And finally, your service bureau is quoted $1986. So 15K, 3,700 and 1986 dollars. So one can understand the importance of DFAM, that is designed for additive manufacturing, right? So, and then you may come across the several processes. The ASTM has standardized these processes into 7. So this is a single step process for polymer printing. So where all the 7 say 3D printing classifications of machines can capable of processing polymers in a single step. So then you have the type of material as a polymer, and the state of fusion, it may be a thermal bonding or it may be a chemical reaction bonding predominantly. And then you have the material feedstock, maybe in the form of a filament, maybe in the form of a melted material, or maybe a powder form, or maybe a liquid, or maybe a sheet or a laminate form. and then how you are distributing this feedstock. The feedstock distribution may be through the filament, and then you may be depositing through the nozzle. So you may be extruding the molten metal. That is exactly the previous speaker has explained. That is a fused deposition modeling. So which otherwise by the ASTM ISO standard, it should be called as a material extrusion process. So that is the one process that you can directly get in the polymer prints. And then you have other one is it may be a melted material. From the print head, you are distributing the material, your feedstock material, and you will be jetting that. So you have a multiple print heads, and then you will be jetting the material, and then where your parts are ready through a material jetting system. So here you are using a jetting technology rather than extrusion-based system here, right? And you may have even a powder as a feedstock material, and you will be distributing either in the form of a bed or a print head. You will be say spraying it, or you have a selectively fusing the material here, the powdered material. Selectively you are fusing it, and that is called as a powder bed fusion system. And if you come from this, is the binder jetting system, where you have the binder will be jetting from the print head, and you have the feedstock material as the powder. So then you're going to get the bonding between the powder particles to this, a binder, or rather than a kind of adhesive that you're going to use here and get the bonding. That's called binder jetting system. And you do have a chemical reaction bonding, maybe a liquid, maybe you may be printing through a print head, this liquid photosensitive polymer resin, typically it is, and that is a light reactive polymerization process may undergo here and it's getting cured. So that is through a material jetting technology or a VAT photopolymerization process. And at last, like you have, so another chemical reaction bond kind of a thing, a sheet or a laminate can be stacked together and fusing of these stacked sheets. So this is called a sheet lamination process. So all the 7 processes can capable of polymer printing in a single step. And coming to the metal, so metal directly you could be able to process only through 4 categories of 3D printing or additive manufacturing machines. So that is either a DED system, that is direct energy deposition, or material jetting, powder bed, or a sheet lamination. So, and then why I'm calling this single step means you can even say some of the metals or some of the technologies, even it may go in a 2-step process or 3-step process, means you are going to get some green part, and further it has been done in infiltration, debinding, and then finally sintering in the furnace, you're going to get your final metal part. But here, all these technologies can capable of printing in a single go in the metal part. So it's a metallic part here. The state of fusion may be a melted state or solid plus melted state or solid state. And your feedstock material may be filament, wire, or powder, or a sheet laminate. And then you will be distributing the material through a nozzle or a powder bed you're laying, or a sheet or a laminate that you're bringing it your feedstock, right? And then you have basic principle here. Selectively, you are depositing the material to substrate. So you may use the energy source here as electron beam or a laser or some inductive heating. So then you have a directed energy deposition technique or a material jetting system under this category. Or you do have a powder-based feedstock material here, and selectively you will fusing it and either use electron beam or a laser. So you'll be called that as a powder bed fusion. And coming to the last process of solid state, and you do start with a sheet or even a rod or even a wire can be the feedstock material here, and you will be fusing that, and you will be stacking it, and you may using some sort of ultrasound or some solid state welding is also being used here to get the bonding or to stack those laminates, right? So this is the metal direct in a single step you can get it. So then let us focus on to the capabilities of this AM. The part consolidation is the biggest advantage once you come to migrate from the conventional to AM process. So I will try to explain some of the case studies that has been, or literature saying that, so how the GE has so made this leap engine nozzle. So their traditional design was, it was 20 parts. Now they made it as a single part. So, and then this leap engine part, so they are producing, so maybe around 40K per year, and they already shipped it. And the biggest advantage is 95% inventory reduction. So it is only the digital inventory. You know, that's what, once you migrate to AM, so then you have the inventory is 95% reduction. and weight reduction has happened 25%, and you have a cost effectiveness is 30%, and it's 5x durable. So you can understand the capability of EAM. So how it has been used for the consolidating the parts, and what are the benefits that the aero industry or even any other industry that you are looking at some part consolidation. This is the part, so which it consists of some 16 plus parts, and then that's a conventional assembly in a vacuum form. And here it's a duct has been consolidated through additive manufacturing. Now it is a single part. So the advantages or the drivers, the easy to design, less supply chain, no tooling, and less labor, no assembly error, less certification, the lighter product, and you have a better thing. And even you have other say case studies saying that the part consolidation here has happened 100 parts to traditional design to additively manufactured single part. So then traditionally they used to do a brazing and EDM. Now the lead time is 8 months to develop, and now it is because of additive manufacturing, it is a fewer weeks to complete. And 95% reduction in weight and 20% reduction in production cost and 75% in the non-recurring cost has been eliminated. So because of this EAM. And this is another case study from again GE. So the 300 parts, now it has been to single part, and 7 assemblies leads to a single assembly. So, and the weight reduction has also happened. So which you can see all these parts as made in a single part, right? So that's what where your EAM is shining, wherever you have a lot of part consolidation, which your industry is looking to have such products. So again, GE has even made this kind of a catalyst engines. So they have targeted, even there, 1/3 of these engine parts are done through additive manufacturing. So this project they started in 2015, and recently they got the certification from FAA. So, and then the advantages, more simplified supply chain and simplified assembly and simplified maintenance and weight reduction, and also improved fuel burning efficiency, and you have 10% more power. So these are some of the advantages that you are going to get for the part consolidation. And of course, maybe several people, maybe from tooling industry, so where you have conformal cooling channel is the biggest, say, driving force for AM application is concerned, right? So as we know that the conformal cooling channel through a conventional methods, like you can do only a straight drill, but whereas here you can confine your channels, which is the product that you are looking at. So that's what where this AM is shining in conformal cooling design. So where, as we know that your cooling time, so 60 to 70% of your time goes to cycle time reduction. This because of this, say the conformal cooling channels, right? So then it is confining to the shape of the product that you are fabricating it. So this is the biggest advantage for a tool making industry, that they are integrating this AM to the tooling industry. And in continuation with that, your conformal cooling channels, so which have a better heat distribution, like the conventional cooling channels versus your additively manufactured conformal cooling channels. So where you can see the distribution, the heat distribution, and where you can see, say, your internal stresses has been minimized, and you have ultimately the quality has been improved, and you have reduced the warpage, shrinkage, all that problem, right? You can precisely control your plastic solidification in the mold, and where you can minimize these distortions or the shrinkage problems that you come in a traditional way, right? So, and yeah, this is another case study, like where you can see the conformal cooling channels or that are designed in the product, and ultimately it has been printed in one of the metal AM systems. It's in a single step, designed to the tool in a single step that is possible through additive manufacturing. So this is another a research paper which demonstrated here. So this is an automobile headlamp part. This is a case study, so which has been published in one of the articles. So where you can see you see the cooling channels now, the additively manufactured or conformal cooling channels versus the traditional cooling channels, and where you can see even the numerical simulation results showing the better one, and you have a better improvement in the, say, reducing the warpage and the stress mean temperatures. So all that, so which you can be able to get all these advantages versus your traditional, say, your tool designs, right? So this is one of the research articles saying that these benefits. And even you have the improved cooling efficiencies is another case study. It has been done. So it will enable you to come out with a kind of innovative kind of a mold design. So like even to accommodate these support structures. So then that's what your design for AM is going to play a major role here, like how you are able to tackle these self-supported, designing the self-supported say structures for this channel, right? And further lattice-based designs. So lattice-based designs here, which you can see, and it will improve the cooling efficiency of the tool, right? Say where your additive manufacturing is going to play a major role under this. And of course, topology optimized structures and bionic designs is very much connected to the additive manufacturing. So where you can optimize your product topologically or your generative designs. So as or even bionic designs, all that has been done in a single shot with additive manufacturing technology, right? So any structures is topology optimized, lattice based, bionic designs or lattice structures, or anything that so it can be easily done through additive manufacturing, and you follow the guidelines, design guidelines. We'll discuss that guidelines very quick manner. We don't have much time, so we'll quickly discuss that also. We do have a certain topology optimization. Is the software, and coming to the build simulation. So you need to have say this is say the support structure should be optimized, right? And we do some you have a certain model, say it is getting say distortions, residual stresses. So it has been built inside. So how do you get optimized this and suggesting some say distortion compensations or model optimal supports, or even it will minimize the risk for the printer damage. So this is for the metal which we have at our facility. We have this metal machine. So where we are using this for the simulation of this metal 3D printed parts. Even it will predict the post processing like a heat treatment, stripping, support removal, all that. So, and then I have listed some of the simulation softwares for additive manufacturing, both for polymer as well as metal, say practice. So you have a lot of software from these, say, the software developers, right? From the ANSYS, 3D Systems, all the Autodesk or Siemens or Additive Works. So I might have missed some of the commercial softwares also. You can find a lot of some commercial software nowadays. Much emphasis on the simulation of these multi-physics based simulations of this AM related stuff. And let us focus some time on the design rules for the polymer AM technology. So the biggest challenge here is anisotropy. So the anisotropy is the biggest challenge for additive manufacturing, especially the polymers, and it will vary from process to process. So extrusion, it may have a different ball game here, and it is a VAT-based system or material jetting system. You have a different ball game here, but anisotropy, which we need to say tackle here. So your design, so your orientation is matters. Like some extent, you can minimize this. So this orientation may be weak or almost like certainly it will break. But you change the orientation. So like that, it may be this orientation may give a better compressive strength or the spring and the strong hook. Or this orientation may even lead to some other benefits, like which we need to understand. So then we need to fix the right orientation to tackle this, right? And even the wall thicknesses, like say you try to minimize these, say in the lightweight consumer products, it may be 0.6 to 2.5 mm, or heavy duty industrial products, it may be 3 to 5 mm. And just you maintain the 10 degree, which you can say minimize a lot of large flat surfaces. Otherwise, it may lead to a lot of distortion. So like, then which we need to follow certain guidelines, then it will save you these kind of say problems, right? So one, and of course the other issue is the support structure and the overhang. So then your angle, then this will matter a lot. So if it's 10 degree and you have a different support structure, or 45, 50, so then you have a different support structure altogether. Then we need to understand, we need to optimize this kind of the support structure and the overhangs in your design. And then your build orientation will also dictate your support material that is going to consume. And you have certain areas, like if the area is less and your supports may not be required or minimal, then which we need to work on these, then only you are able to optimize this, right? And this is one of the part, like say how your thickness of the component is getting affected, even the minimum size of the hole, right? So you have 2 thick, you could be able to realize all 0.5, 0.8, or even 1.5, 2, everything is realized. But at the moment you increase the 2 to 4 as a thickness, so where you can see it 0.5 it got a problem here to come out this hole, right? And similarly, if you increase the thickness, so you have certainly, so which we need to understand, then it may vary from machine to machine, material to material, but we need to understand that how it is, like then you should not miss any of your future, right, in your product. And of course you do have some ribs that should be had some design rules, so then which we need to follow those design rules, on which we need to make it very, say your thin ribs should be carving down to a kind of this kind of a thing, and which we need to follow certain guidelines here to be. And then you have some sort of especially like a powder bed system or a vat based system, so there will be a say material that will be there inside. If you are making this kind of a part, then you need to provide some salt shaker holes to remove that material. So then which we need to understand these design rules and accordingly. And that is some of the design rules I kept it here. And coming to the metal, so you have a different ball game here altogether. So then again, we need to compensate your layer, what you call your laser diameter, similarly like how you are doing the tool length compensation or tool diameter compensation in CNC technology, where we need to say compensate this beam offset in your say metal system. It's a laser based system, and which we need to work on the parameters like hatch space, and which we need to work on the parameters like a contour spacing, and which we need to understand this. Otherwise you may be ending up with a kind of errors or the kind of challenges here which you will be facing it. And you may have a different energy beam scanning strategies, it may even useful to say come out with some sort of solutions for your situation, where sometimes the more residual stresses inside it has been built, or the shrinkage, warpage kind of a stuff, which you could able to manage by varying these parameters, right? And you have unsupported angles, like say you have a CAD part, and if it is 50 degrees, then absolutely no problem. It doesn't require any support. And 45 is also okay. 40 is okay. But if you once you have a lesser angle, when which we can see how the parts are getting, say, not coming because of your support structure is very much needed here. So one can understand these kind of say limitations or the guidelines which we need to follow. And you have unsupported overhangs, like again you can see 1.2, 1, 0.7, 0.5, 0.2, 0.1, and we need to understand these kind of things, features in your design, and accordingly you need to. Otherwise, you maybe end up with a difficulty, right? And unsupported say bridges here, if it is 1 mm, 2 mm, it's fine, but it is 3 mm, 4 mm, 5 mm, which you can see. So how it is coming, like so which we need to understand these kind of say dimensions that you are working with, this sort of things. And another major challenge here is the residual stress. So if you see the effect of the residual stresses on the metal-based AM system, the support material, mod material, it has been peeled out, right? So it's not strong enough to say the support as well as the model, or even model has been splitted here because of the residual stresses that has been built inside, right? And you have a certain say the scan patterns which you can say use these scan patterns accordingly. Like say you have a mandate kind of hatch pattern here, which is a high build rate and high residual stresses and suitable for small or the thin parts. And you have a strip kind of a hatch pattern. This is meant for medium build rate, medium residual stresses, and suitable for very large parts. And you have a chessboard or checkerboard kind of hatch pattern, which is a slow build rate, but you have a lower residual stresses and suitable for very large areas. Like once we need to understand these guidelines. And another thing, like where the residual stresses because of uneven thicknesses in your design. So which we need to work on those, like we try to make it a uniform say thickness across the product. That may give you the solution. So not only that, because of that, so it will also reduce the weight and it's also reducing the residual stresses that has been built inside this, the product, right? Say, and you have the redesigned small clamps here, so which is with the even wall thicknesses and no areas where the stress can be build up, say, and 25% reduction in the weight from the original design, right? And then these are the parts which is printed with the supports, which you can see these how now nicely just come out, right? So once you are working these kind of systems, we need to understand these guidelines of the design rules. And yes, stress concentration is another major thing here, which we need to say do a sort of say we need to tweak this. Don't leave a sharp corners. Then we need to do a slight tweaking in your design. And even this, you need to go with the filleting. So because of this non-uniform thickness, so it may lead to a sort of what you call the deformation or the stress concentration here. You come out with the filleted corners, so that will reduce the stress concentration as well as your say the residual stresses can also be minimized. And coming to the horizontal holes, you have a certain limitation, like say 2 mm hole, it's fine, it's coming good, 4 mm fine, 6 mm fine, 8 mm, but slowly you can see once you are increasing the diameter of this the hole, which it is not coming out better, right? Say without supports I'm talking about. So if you are looking this kind of a thing, then definitely we need to understand what is the threshold value or what is this constraint about this, right? And then you may have a solution for this also. We need to design for additive manufacturing where we need to understand, we need to slightly tweak these designs. Maybe 8 mm hole, circular hole, absolutely fine, no issue. But it may vary from machine to machine, material to machine also. And elliptical holes, maybe the height 20 mm, up to that it's fine. And say teardrop shape is always the better. Like even it could be, even you go, again, that depends on this angle also, right? And then you have a diamond shaped hole. So like that, which we need to understand these design guidelines or the design rules for additive manufacturing. So even for positioning of these, say parts, so this is the recoater where this is the recoater direction and this is the part you're fixing it. And it's better to avoid your recoater and the part is on the parallel, like better you keep it in some inclination. That will be the better to organize your say parts. And don't line up the parts like this, but you give some spacing, right? Like this, but not in this way. Don't line up this. There will be your recoater and this part will be organized in this way. And then even you can see if you are not following that, so then you may be say come out with the defect parts here, which is damaging. Some recoater blade has been hit here, because of that it has been, your part has been damaged, right? So which we need to understand these guidelines. And you have very taller part, then better you put as close to the as recoater. But you have but don't keep away from the recoater, and better you keep it very near to the recoater, right? So these are some of the guidelines that, and you have design for additive manufacturing guidelines from the Purdue University. So I have another couple of slides. I'll quickly warp of the presentation, right? So, and then you have certainly a Purdue University, they have given some sort of design guidelines here. So they made some matrices, like they were based on the complexity and other parameters. So they have designed this. So it will be like for the functionality and the material removal, unsupported features, and the thin features, the stress concentration, and tolerances, and the geometrical exactness. So they have divided this. Just you can scan your design through this, and you will get the score. And if the score is very less, and you may not be much worrying about the redesigning or modifying the product. Like say, if your score is high, then which we need to redesign or which we need to consider for the redesign. So there are certain platforms where you can find this kind of design for say additive manufacturing guidelines. So let me summarize my talk and let me conclude my talk. Actually, you have several parameters. This is a Ishikawa diagram or the fishbone diagram, and this is targeting to a metal AM system, but it may be very well applicable for the polymer printing also. Like where operator, sorry. Hello? Yeah, sorry for that. So where the operator related parameters may be the one area where operators should be follow some cautious and expertise and some experience. And coming to the pre-processing kind of area, like where the part positioning and you have the part orientation, slicing, and build setup preparation. So you have a lot of parameters that we need to consider in that area. And while processing, so maybe the scanning parameters, laser parameters, so which we need to understand. And then you have the gas supply and then all that. And post-processing, during post-processing also, you have a lot of parameters that it's going to judge your part quality. And we need to understand this, and accordingly, we need to work on this, right? And even you have, say, the part related, maybe CAD or your CAD geometry, and you have a mechanical components, AM systems related, and gas supply management, inert gas or vacuum, all that. And then you need to check the condition, and you have optical components, like you have a scanning, say you have a mirror there, and the optics of that, it may even affect your part quality. And ultimately your feedstock or the material, so it's the metallurgical properties and your handling size, rheology, rheological properties, right? And chemical composition, mechanical properties, powder characterization, then thermal material characterization. So all that will affect your part quality, right? So which we need to say understand this. And let me summarize what I have done for this session. So we started with the design approaches in additive manufacturing, and AM process plan and AM processes, and part consolidation, that with the additive manufacturing, and conformal cooling channels. It's important concept here with the AM, and topology optimized structures, bionic design, and build simulation in additive manufacturing, and design rules for polymer printing, as well as design rules for the metal AM. So we have the AM facilities at Native Warangal. We have a metal 3D printer, and we have a couple of Stratasys make machines, that is say Dimension series and Mozo series machines, the FDM based technology. And we have desktop 3D printers, Ultimaker and other desktop DIY kind of printers. And we have AnyScan and SenseScan, and we have muffle furnace short pinning for post processing of the metal 3D printed parts. And we have AM software like Mimix, Magic, Thematic, Catalyst, and 3D Expert. These are some of the facilities we have at NIT Warangal. And we are the people started MTech in additive manufacturing with collaboration with CMTI in 2014. We started this program. Now we have self-sustained. We are running by our own this program from NIT Warangal. So yeah, actually I have done from my side. If you're having some queries, clarifications, so then I will be very much thankful. So I will be handing over to you, madam.
Yeah, thank you, sir. Thank you, Professor, for this. This was really elaborate discussion on the technical aspects of 3D printing, and the design criteria was explained in real detail. I think all the participants would have very be informed about the nuances in designing the things based on how to optimize the parameters while you design a particular product in metal or polymer. And thank you so much, Professor. So
Thank you.
I think we can have the question and answer session now. Participants, you can either put the questions in chat box or you can raise hands. So I just have one question to Abhishek sir.
Yes, ma'am.
Yeah, is there what is the prospects of 3D printing of forms? Like, what are the challenges, and how far we can go ahead with the 3D printing of forms?
Of foam?
Yes.
FOAM.
FOAM, yes.
No, I'm sorry, I don't know about this.
Okay, okay.
However, I read something long back that there is one technology that has been developed around it. Maybe I'll find it and get back to you.
Okay. Professor, do you have any suggestions?
Regarding foam printing?
Yes, sir. Foam 3D printing. Because when you consider this lightweighting, so many people are working on foams as well when in the material aspect.
no, my suggestion would be like foam printing may not be that much encourageable through 3D printing. Maybe,
Okay.
yeah, maybe better. You may have other conventional this thing, cutting, carving, or
Materials.
maybe, yeah, maybe that may be, yeah, maybe otherwise secondary process like we can try, but not direct
Okay.
single thing. Yeah, that is my
Okay.
idea on that.
Yes, sir. And one more question. This 3D printing of continuous profiles. Like, can we overcome the limitations of printer size? Like we are now confined to a particular product, maybe large or small, but is there any chances of having a continuous profile?
That question.
I'll
Yeah,
answer
yeah.
that question, and then maybe
Yes,
Sir can also answer. So the short answer to that question is yes.
Okay.
Big area additive manufacturing has been developed. For example, Stratasys itself has a printer which is called continuous build demonstrator,
Okay.
which essentially prints on a conveyor belt. So there is there is limitation on 2 axis. I think it's about 1 meter by 1 meter, but the third axis is almost infinite. And then there are, but today that's $1 million machine. And then there are some, desktop type versions of those machines. One is called Black Belt 3D, if I'm not wrong. But then again, the XY is much smaller. So the technology does exist, but industrial technology at affordable price,
it's
still not there. Yeah.
Okay. And Professor, any suggestions on this?
And no, actually, I do agree with Dr. Abhishek. Yeah.
Okay. So we have few more questions from the audience. Mr. Mariappan, he has asked if there is any limitations in DFAM technique, and whether you please clarify this, whether these method can be applied to all products without affecting its efficiency. He's asking about the DFAM technique.
Yes. Yeah, DFAM, that is, say, again, now the major challenge here is like you have a very limited standards here in AM. As on date, it was say printed around, say published around 35 to 40 say standards by ASTM or ISO together. Say coming to DFAM rules, so that is like where it will vary from process to process also, not like application. Yeah, of course. So now you can see application wise also, which we need to work on that. So which we need to understand the capabilities and constraints of the machine first, and then of course your design that the application also, right? So DFAM, it is like which we need to customize, or again it depends on it's very tough to answer your question, but definitely DFAM will have I cannot say that's 100% it is, but again it depends, it's subjective, like where if you even change the material, you cannot generalize this. So each material will behave differently with your laser source, if it is a laser machine, or even it could be anything, like which we are not able to generalize that, and hardly you can find the standards in this area. So yeah, so then which we need to work each thing as each application. Yeah.
In extension to what Sir is saying, I'd like to add this. See, DFAM or generative shape design is heavily material driven. Okay, but the softwares are intelligent enough that if you put the process, tell it whether it's DMLS or SLS or FDM and which material, and put a weight target, it can not only design but also simulate whether this is going to work or not. So there are several parts that are being done using DFAM, which are parts which have a life cycle of 10 years plus. That means the part has to be staying in its environment for 10 years. So simulation is combined into DFAM to make sure that whatever you are designing is not just arbitrary, but it actually works. So doing manual DFAM is not recommended, especially when you are looking at a weight reduction application. You must always use a validated software, could be Dassault, could be Altair, could be Siemens, whatever, which simulates the process and tells you whether the part is going to survive the loading conditions or not.
Okay. Okay, thank you, sir. We have one more question from K. Niranjan Rao. He's asking what will be the future of CNC machines with if you compare it with 3D printing?
Uh, that's an interesting question. See, eventually, I will not say CNC machines will get eradicated, but additive will replace a lot of the work that is happening with CNC machines. Say today, the challenge is that 3D printing is still a bit slower, and part characteristics are not uniform always, right? But homogeneous 3D printing technologies are being developed, as well as technologies are being developed where it's a co-system. So additive plus attractive combined. So I think this is where things will go on in the future.
Okay, okay.
Yeah.
Yes. So, audience, any more questions? Any more questions?
I think somebody had put a question that somebody wanted to come see your facility. So maybe you could put an address on the chat box.
Yes, sure, sure.
And your phone numbers and all of that.
Yeah, we'll get that. Okay, sir. I think there's no more questions from the participant side. So I think we can wind up the sessions. On behalf of CIPET and Altum, I would like to thank all the speakers who have taken time out of their busy schedule to enlighten us about the perspectives of additive manufacturing, about the technical details of 3D printing and other nuances which to be taken care of while designing for processing as well as post-production. And thank you, Mr. Abhishek Kalra and Professor Ravi Kumar. Thank you so much.
Lakshmi, this is Nagesh here from Tata Elxsi.
Yes, sir. Yes, sir.
Sorry, I could not make it in a time. I just joined and completed. Is it possible to get a recorded one?
Pardon? Yes, yes.
Is it possible
I'll
to
just
get
let you.
a recorded one? Yeah.
I think it's possible, sir.
Yeah. Hi, Abhishek.
Hi, sir. How are you?
Sorry, I got stuck with some urgent work.
No worries.
I could not join in the beginning.
No worries.
Yeah. Fine.
We can always discuss.
I will see the recorded one.
Yeah.
Thank you.
Okay. Okay, sir.
Yeah. Okay. Thanks.
Yes, sir.
Thank you.
Yes, sir. So once again, thank you to all the speakers and participants who have patiently listened. And I think most of you would benefit from whatever our speakers have told. And you can always be in touch with Altum, Professor and CIPET in case of any requirement. So I'll put across the CIPET's address in chat box. Okay. There's one more question from Akshar Chandra. He wants to know more about DFAM printers. He's asking how do he get to know more? Abhishek sir?
Hello.
Hello.
Yeah, sir, this was the question to Dr. Ravi, sir. Actually, while he was discussing about DFAM, so there were some pointers he had discussed, which I couldn't make a note exactly of, but he was talking about part consolidation designing. So, I wanted to explore more about part consolidation designing, as I have been a student of 3D printing and have been, doing very basic CAD based designings for, 3D printing and all. So I needed to know how. I needed to explore it more. Could you give me any guidance on, like, how I could explore more on DFAM? Like one of the pointers which I could have noted was, one thing was part consolidation designing. I needed to know what are the processes through which, or the exercises through which you actually consolidate the design and all. Like,
Professor?
Yeah, hello. Yeah. No, actually, can you elaborate that question like from the participant who asked the question? Actually?
Yeah.
Pointers?
The question was that while you were discussing about DFAM,
Hmm.
it was mainly about part consolidation designing, right?
Right.
Or there were other points also involved in it.
Yeah. Okay. Yeah, actually, then what is his requirement exactly and the application, and accordingly, then it should be done. It is not. So that's what I'm asking. What is the specific?
Yeah, the question was, sir, that how could I explore the various techniques through which the consolidation is being initiated for, various conventional designed machineries or tools, jigs of fixtures and all,
Yes. No, actually, you cannot get in this in a single place saying that all the processes explained. But I can suggest some handbooks which you can refer also regarding this. Yeah, you can mail me, then I will share or I will provide that resources regarding the handbook, the guidelines for this additive manufacturing for various processes.
Sure.
So, yeah.
So could I get your email address, sir?
Yeah, mine. Yeah, YRK.
YRK
@nitw.ac.in.
nitw.ac.in.
Yes, yes.
Okay, okay. Thank you, sir. Thank you, sir.
Yeah.
Any more questions? I think there are no more questions. So thank you so much. Thank you, speakers. Thank you, participants.
Yeah, thank you, madam. Thank you for
Yes,
the
yes, sir.
opportunity for you and Dr. Ben Singh.
Yes, yes. Actually, he was like expecting to join us, but somehow there is some, he is traveling right now, so he is unable to make it.
Okay.
Yes, yeah.
Thank you.
Okay, sir. Thank you so much.